All right, let's go over this. All right, we are going to draw this molecule. It says OCN. Luckily, minus. This one is in the order that they go in. So that's not always true, but this one works out. Okay, so the first thing that I'm going to do is I'm going to count how many valence electrons I need to show. Remember, we're talking about valence electrons, not total. So this is, oxygen is 6. So we're going to count the column skipping the transition metals. 1, 2, 3, 4, 5, 6. Oxygen's column always has 6. Carbon's column always has 4 valence electrons. Yep. And nitrogen is 5. So this minus, do you remember what this minus does? Good, we get 1 more electron. So the minus sign gives us 1 more. So then we're going to add this up. So 4 plus 1 is 5, plus 5 is 10, plus 6 is 16. So then we need to figure out how we're going to draw this. So pick the central atom, and then you're going to connect the atoms to the central atom. So remember, every bond shows 2 electrons. This is 2, 4. So we have now shown 4 valence electrons. 4 valence electrons. We need to show 12 more. So the first thing you're going to do is you're going to fill the atoms around the outside. So I'm going to put them here. 2, 4, 6, 8, 10, 12. So these ones, now we've shown 12 more. We've shown all of the valence electrons. There's no more. But remember, each atom wants to have 8 valence electrons. So here, oxygen has 2, 4, 6, 8. Nitrogen has 2, 4, 6, 8. But carbon doesn't. Okay, this one is a weird one. We have to pick which one's going to share. If they're identical, then so the other one that comes up is like CO2. And we just make both of the oxygens share, and then there's double bonds. This one's weird because we're going to make nitrogen share twice. Because oxygen is more electronegative, it wants to keep its electrons. Nitrogen, we're going to make it share twice, so we're going to make... Yep. So then carbon is going to be like this. C triple bond to nitrogen with a lone pair, and then oxygen. Remember, this was an ion. It had a negative charge. Oh, you can't see it. So we need to show that. This, somewhere in here, there's an extra electron. There's a negative charge on the molecule, on this ion. So now, again, we can check. Nitrogen has 2, 4, 6, 8. It can see all the bonds. Carbon can see the bonds, 2, 4, 6, 8. Oxygen can see 2, 4, 6, 8. So everything has 8. We've shown that it's an ion. That's how we draw that one. Questions on that? Okay. All right, let's go back to Alex, and we'll pick up where we left off. So I'm going to pull a few things up here. Let me pull up Alex. Let me pull up some slides that we might see. Let me see if I can find my list of topics. All right, you guys, we got the pictures, right? Determining, we recognize acids and bases from a sketch. Yep. Is that true? Okay, so the next one on our list is determining the strength of an acid from a sketch. I don't think we've done this, all right? All right, so we have to remember back to, I think it's chapter 6, where we talked about equilibrium constants. So this is the same kind of thing. We're looking at where does the reaction lie? Is there more product or more reactant? So in chapter 6, we looked at the equilibrium expression, and we looked at the concentration of each product over the concentration of the reactant. Does that sound familiar? Okay, so we're going to do the same thing, but instead of products and reactants, we're going to be looking at the acid and base reaction. So the reaction we're thinking about is we start with some kind of acid. This is our acid representation of an acid. And then it splits into H plus and the conjugate base. Okay. But remember, Alex likes to represent H plus with H3O plus. Okay. So the hydrogen is going to find a water, and so this is the hydronium. This is the product. Okay. So these are our products. So the acid reaction equilibrium constant for an acid is the products, the concentration of the products, H3O plus and A minus, all over the reactants, which is HA. So we're going to be looking at a picture. What we're going to be looking for is the H3O plus. So we're looking for something that looks like hydronium. And we're looking for the conjugate base without a hydrogen. And then we're also looking for the conjugate base with the hydrogen. So that's what we're looking for in this Alex. And then we're going to rank them. So we're going to find the value, and then we're going to see, okay, which one is the strongest? Which one is the weakest? The bigger, the more towards this side they are. If they're going towards this side, they're going to be stronger. Okay. If we have no HA left, do you remember what that was? If all of these are gone, then it's a strong acid. That will be our strongest acid. They will only give us one strong acid. So if we don't have any of this, we're dividing by 0. That's illegal. If there's none of this left, then it's going to be a strong acid. Let me use this other one. Okay, so let's go to the picture. So my picture, I'm going to count hydronium, conjugate base, and then original acid, the conjugate acid. So hydronium, 1, 2, 3, 4, 5. So let me see, how are we going to do this? Maybe I'll just put it over here. We'll have to. So for number 1, we have 5 hydroniums times 5 conjugate bases. They should be the same. 1, 2, 3, 4, 5. Conjugate base, 1, 2, 3, 4, 5. So the ones without the hydrogen is the conjugate base. So that's 5. Over, let's not put that. The original acid. There is one original acid. So that's my original acid with the hydrogen connected. So that's a 1. Okay, let's look at the next one. Number 2. Number 2 is, we have only, can you see how we have only the conjugate base? There's none of this with hydrogen. So this one is going to be, we would be dividing by 0. This one, we're going to say this one's strong because they're all dissociated. Okay, number 3. Let's see. So I'm looking for hydronium. 1, 2 hydroniums times conjugate base. 1, 2. That should always be the same number. So that's good. It's the same number. And then how many original acids? 1, 2. So the acid connected to the hydrogen. So 1, 2. So this is just 2. Okay, that one was 25. Oh, and then the last one, let's see what we have. Look for hydronium. 2 hydroniums times by how many conjugate bases? 1, 2, okay, also 2. Should be the same. And then the acid. How many original acids? Okay, 1, 2, 3, 4, 5, 6. So 2 times 2 divided by 6. So that's what? 4 divided by 6, which is 2/3. All right, so then we're going to rank them. If it's a strong acid, that's going to be our strongest acid. And then we go by number. This one's the biggest number, so that's second after the strong acid. This one has a bigger number, and this one has a fraction, so that would be 4. So then we just rank them. So number 2 is the strong acid, that's the strongest. 2 is the biggest number. 3 is the next biggest number. And 4 is the fourth biggest number, the weakest acid.
So biggest number, strongest.
Yes, biggest number is strongest.
So if it completely attaches, so 0, that makes
divide by
the biggest
0.
number inherent. You can't get bigger.
Yep. Yep, good. Okay, questions on that one. Should we do another one? Okay, let's do another one. All right, solution 1. Okay, we're doing the same thing. Where's my piece of paper? Okay, we're using this equation. We're looking for the, let me see if I can fit 2 up here. Ka, the equilibrium constant of the acid. All right, so I have 1, 2, 3 hydroniums. So that means I better have 3 conjugate bases. Let's see if we can find it. 1, 2, 3. Yes. Over the conjugate base, no, the original acid. 1, 2, 3. So that's 3. Okay, so that would be, my value is 3. Okay, number 2, let's look at, oh, I would want it to fit right here. So look for hydronium. 1, 2 hydroniums. So I better have 2 conjugate bases. 1, 2. I'm going to divide by the original acid. So that's still with the hydrogen. 1, 2, 3, 4. So 2 times 2 is 4, divided by 4 is 1. Okay, let's look at the third solution. My third solution has 1 hydronium. So I better have 1 conjugate base because that's where the hydrogen came from. Here. So this hydrogen gave the water a hydrogen. Okay, and then we're looking for the original acid. 1, 2, 3, 4, 5, 6, 7. So this is 1/7. And number 4, let's see what we have. We have 1 hydronium times 1 conjugate base over the acid. 1 acid, 2, 1, 2, 3, 4, 5. Okay. 1/5. All right, so biggest to smallest. So this one is the biggest number for me. That's going to be the strongest acid. Then 1 is not a fraction, so that's going to be the next biggest number. Okay, and then I think 1/5 is bigger than 1/7. So this is going to be the next biggest acid or strongest acid, and then this is going to be the last strongest acid, weakest. All right, so 1 is the strongest, 2 is the next strongest, 3 is the weakest, 4 is the third strongest. Okay. All right, do you want to do another one, or are you ready to move to the next topic? Next topic, are you ready? Okay. All right, we're almost through. Let me remember which topic. Okay, next one is calculating the pH. So I'm going to find that in here. Calculating the pH of a strong acid. Okay, let me write some notes, and then we will do the Alex topic. All right, so when we are calculating pH, we're going to use this equation. The pH is equal to the negative log, so this is log base 10, of the concentration of hydrogen ions. Okay, so remember, chemists, instead of saying concentration of, they use these brackets. So anytime you see these brackets in chemistry, we're talking about concentration. Yep, concentration of that. All right, so we need to remember that concentration of hydrogen, concentration is moles of hydrogen over liters of solution. So the first thing we have to do is find this, and then the second thing we have to do is plug it into our negative log formula. So not too tricky, I think. Shouldn't be too bad. So just pay attention here, practice this one a little bit, and it's not too bad. All right. So this one, you have your list of common acids and bases. Did I put you another one? I can't remember. Okay. So this, you have to know these for this question because you need the formula. It's going to give us a mass. We have to divide by the molar mass, but we're not going to get the formula. We have to memorize the formulas. So for example, it says, a chemist dissolves 167 milligrams, which is very dumb. No one ever measures acid with milligrams, I don't think. Okay, so 167 milligrams of pure hydrochloric acid in enough water to make up 330 milliliters of solution. Calculate the pH of the solution. Okay, so they're going to give us a mass. So we're going to take the mass. We're going to make sure that it's in grams. We're going to divide by the molar mass. We have to know the formula to find the molar mass. That's going to give us moles. And then we have to make sure that the volume they give us is in liters. And then we'll have moles divided by liters. This one they give us 167 milligrams. I'm going to first convert that to grams. So 0.167 grams of hydrochloric acid. What's hydrochloric acid? Yes, good. HCl. And then we're going to divide by the molar mass. I'm going to use my Alex calculator for that. So I'm going to add hydrogen and chlorine. I just think it's super nice on the Alex calculator. There it is. So 0.167 grams divided by the molar mass of hydrochloric acid, which is H plus Cl, one of each of those. Close this box. Okay, hydrogen and chlorine. Now this is the number of moles in the solution. This is the number of moles of hydrogen. Okay. Do you remember last time we had to think about how many particles something split into? I don't think that we will see that in this question, but this hydrogen, there's only one hydrogen for every 1 mole of acid. This is a 1-to-1. Let me give you a different example. If I used H3PO4, this potentially could give me 3 hydrogens because I have 3. So I would have to multiply that by 3 because I could potentially have, this one's a weak acid, so they don't all split off. But maybe H2S is, this one's a strong acid. We get 2 hydrogens out for every mole of acid. So we would have to multiply the number of moles by 2. Okay, that's going to come up in the titration question next time. I don't think it'll come up in the pH question. All right, so we've divided by the molar mass, and we've got the number of moles of acid, but this is also the number of moles of H+. Does that make sense? So this is moles of hydrogen. Because this is strong acid, for every one of these I get an H+. All right, so then we need to divide by the volume. This is 330 milliliters. I'm going to divide that by 1,000 to get 0.33 liters. And then divide my moles. So this, now I'm doing this. This is moles. I'm going to divide by my liters. 0.330. This now is my concentration of hydrogen. So now I'm going to stick it into this equation. So now that I have the concentration of hydrogen ions, I'm going to do log, but it has to be the negative log, so let me put the negative in the front. Okay. There's one more new thing with log. So I'm going to write this number down, 1.8574. Oops, 1.8574. Oops, 57, what? 8.85754. When I take the log, the number of sig figs I get is the number of decimal places I get. Let's look at this problem. We have 3 sig figs here. We have 3 sig figs here. So when we divided to get the concentration, we should get 3 sig figs. So then when we put the number into the log, we get 3 decimal places. So I guess the number in front isn't really significant. We're counting the decimal places now. So we need to take 3 decimal places. We need to round this to an 8. So my number, if I've written it down right, should be 1.858. I have 3 decimal places because I had 3 significant values above. Okay, that's a new rule. When you do the log, you keep the number of significant decimal places. Okay.
So log is a special case.
Log is a special case, a new case for us. Okay, let's do another one of those. Oops. All right, so we're going to take this value. So this one is, we are taking 379 milligrams. I'm going to first convert that to grams. 0.379. This is now grams of nitric acid. What is nitric acid? Yep, HNO3. So that's one, like this could show up on the test. You're going to have a hard time doing it unless you know the formulas. So you can either fit, if you can fit these on your note card, that's not a problem. But you can also memorize them. Like Alex is thinking that you're going to memorize them, but you get a note card so you can fit them if you want. All right, so then we're going to divide by the molar mass of nitric acid to get number of moles of acid or moles of H+. So let's do that on the Alex calculator. So let's type that in. So 0.379 divide by the molar mass. So we've got H, we need a hydrogen, and then we need an oxygen, and then 3 oxygens. Oops, that was 3 oxygens. A nitrogen. Did I say nitrogen? That was oxygen. I need oxygen times 3. And then plus 1 nitrogen. HNO3Os. Okay. So this will give me the number of moles of hydrogen. And I'm going to take this number of moles of hydrogen, divide by the volume. The volume they give me is always going to be in milliliters. I need to convert that to liters. So 0.390 divided by 0.390. Okay, this is now the concentration of hydrogen. And to find the pH, we need to do negative log of this number, of the concentration of hydrogen. So let's do log base 10, negative log. And then 1, 2, 3 sig figs, 1, 2, 3 sig figs, so my pH needs 3 decimal places. So the pH is 1.812. 3 decimal places. All right, some ways to check this. the pH should be less than 7 because these are all acids. So if you get something bigger than 7, you're doing it wrong. If you get something that's bigger than 4, you're probably doing it wrong because it's a strong acid. So strong acids are going to be pretty low pH. So most of ours are going to be like 1 point something. So that's a good check. Or a lot of students get negative something. Your pH should not be negative in our class. There is such a thing as negative pHs, but for this question, if you get a negative thing, you better check. Maybe you forgot to put negative log. If you didn't forget that, go back through your calculation and make sure you did the concentration right. You should not get a negative log. Your pH should be less than 7. Probably your pH should be like between 1 and 3. Okay? So those are some checks. Do you want to do another one of these? One more. Let's do another one. Okay, perchloric acid. So we got to figure out what is perchloric acid. HCl, is it O4? HClO4? Perchloric acid. So I'm going to first convert to grams, 227 grams. I wrote too far away. Okay, and then we're going to divide by the molar mass. I guess I should put, like, this is number 1. This is the first thing that we do. And then we divide by volume, and then we check for the pH. All right, so 0.227 divide by the molar mass, and we had to know the formula. It does not give us the formula. We have to know that. So we have 1 hydrogen. We have 1 chlorine. And then we have 4 times oxygen. So let's check. 1 hydrogen, 1 chlorine, 4 oxygens. I'm taking my mass divided by molar mass. Okay, so this is moles of hydrogen or moles of acid, but because we only have 1 hydrogen, then it's the same. I'm going to divide by the volume. This is my volume. I'm going to convert it first to liters, divide by 1,000. So 0.130. Oh, it's not on the bottom. There we go. 0.130 liters. So I'm doing this step. I'm taking my moles of the acid I found, divide by the 0.130. This is the concentration of hydrogen ions. Now I'm going to take the concentration of hydrogen and put it into this. I'm going to do the log scale of it, negative log scale. Log, and then I'm going to put a negative in the front. If you don't put the negative in the front, you just have to flip the sign later. That's fine. All right, and then 1, 2, 3 sig figs. 1, 2, 3 sig figs. So my answer needs 3 decimal places. Oh, this one's weird. 1.75. And then we have an 8 and a 9. So we're going to need to round the 9 up. But this one's going to bump to a 6, and then I need another 0 to keep 3 decimal places. Okay. All right. Questions on that? You think you could do that? Okay. All right. pH. That was pH. Okay. Next one is predicting the products of a neutralization reaction. Let's just go to this topic. I think that we will get it. So we're going to do the titration lab. I think it's lab maybe 9. I'm not sure. But we will do a titration. So what we do is we add acid and base, and we want to try to make it equal. We want to add the same amount of acid and base, and that way we can quantify. We'll know how much we added of one, and we can relate that to how much we added of, or how much we had of the other. Yes. It helps us find the quantity, like how strong it was. Yes. So when we do a titration, what we're doing is we're adding an acid and a base, and we can always predict the products of adding an acid to a base, because whenever we add an acid, a strong acid plus a strong base, we always get water and then some kind of salt or some kind of ionic compound. Okay, that's what a salt is. So this one, we start with hydroiodic acid. We add calcium hydroxide. And we can predict what we get out. So what's happening is the hydrogen and the hydroxide are going to combine, and we're going to get water. So you might notice this one we have 2 OHs, and this one we have 1 hydrogen. So we're actually going to need 2 hydrogen iodides for every 1 calcium hydroxide. So then for these 2 hydrogens, these hydrogens are going to combine. It kind of would look like this. Does that make sense? So the hydrogens from the acid are going to combine with the hydroxides from the base, and we're going to get water. Okay. But this one we would get 2 waters because we would need 2 hydrogen iodides. Okay, and then we can predict whatever is left over. Oh, well, we have calcium and 2 iodines. Calcium is the cation. Calcium goes first. The charge on calcium is 2+. And we're going to get iodine. The charge on iodine is -. So we're going to need 2 iodines to balance the 2+ on calcium. So our final formula will be, we need 2 hydrogen iodides plus 1 calcium hydroxide. And that will give us 2 waters and 1 calcium iodide. Does that make sense? So we're always going to have water and then some kind of salt or ionic compound, and then we have to balance it. So this one will have 2 waters, H2O. Make sure you use zeros. Don't use zeros. Make sure you use O's. Don't use zeros.
H20.
Yes, that is wrong. Alex will mark it wrong and I can't give you points back. All right, and then we decided we needed 2 of these HIs to react with the 2 hydroxides. You don't have to put phase symbols in this equation. Okay, let's do another one. Okay, what would our products be here? What would you predict? So we're always going to get water. I just type in water first because I know strong acid plus strong base will give me water. H2O. And we will also get what? What's next? Yep, good. Make sure you put the cation first. The metal goes first. If you can't remember, you're not sure, look over here. Oh, potassium's first over here, so it's going to go first in the formula. Chlorine is second over here, so it's going to go second in the formula. So that would be, if you can't remember, look at what's already happening. It's going to follow the same pattern. Okay, I think people forget to put them in the right order. Okay, and then can you see how we had 1 hydrogen and 1 hydroxide? So we made 1 water. So this one we don't have to balance, or it's already balanced. We didn't have to balance it because it's already balanced. Okay, let's do another one. How about this one? So this one, we would need, can you see how we're going to need 2 H's to balance the OH's? So I'm just going to we're going to need 2 acids to balance this OH's, and then that's going to give me 2 water molecules. 2 waters. Use an O, not a 0. Okay, good. And then barium nitrate. And then can you see we have 2 nitrates, so we're going to need 2 nitrates. But it's because barium has a 2+ charge. Barium's in the second column. Nitrate, that's is a 1-. Yes, you can either remember that from chapter 3, or you can say, oh, hydrogen is a positive ion. Nitrate must have a negative to balance the positive. So this has, just like you said, it has a negative. So then we need 2 of the nitrates for 1 barium. So we're going to write BaNO3. 2. Oops. Okay, questions on that one? Okay. All right. Do you want to do another? Did I just ask you that? Do you want to do another one of these? Okay. I'm not sure if I asked you that one. Okay, let's do another one. So here we have HBr and CaOH2. So I only have 1 hydrogen. I have 2 hydroxides. I'm going to need 2 of these hydrogens in the acid to react with 2 hydroxides, and that will give me 2 waters. H2. Oops. Oh, my caps lock is open. H2O. And then we're also going to get the salt. So we need to figure out what that is. So we've got calcium. Calcium has to go first because it's cation. It's first in this formula. Bromine is going to be second because it's second in this formula. Then we need to figure out the charges. So calcium is a 2+ charge. It's in the second column. So just like this. Calcium is 2+. Bromine is a -1 charge. So I need 2 bromines for 1 calcium. CaBr2. And we also had 2 bromines here, so that will help us balance the bromines. Okay. All right. How are we doing on this topic? Are we ready to do the next thing? Okay. I think we have 1 more topic. Is that right? Or is there more in here? I think we just have 1 left. Okay, we have 1 left. We could do it today, or we're going to take 3 days for this. We could do it next time. Do you want to do it today or next time? Today, next time. Let's vote. How many of you want to finish this one today? 2, 3, 4. Okay, how many want to do it next time? 3, 4, 5. I think today won. So, I think we'll get it done. I think that this was maybe it would be good to do it today, and then we can also do it next time, because this one is kind of tricky. All right, this is the titration equation, or the titration calculation. So this one, they're going to give you the acid because it's going to be a weak acid, and it might be kind of a weird acid. So we have a mass. The student weighs out 0.203 grams of lactic acid into 250 milliliter volumetric flask and dilutes to the mark with distilled water. He plans to titrate the acid with 0.1400 molar sodium hydroxide. Calculate the volume of NaOH solution the student will need to add to reach the equivalence point. So what we are doing is we want to get to a place where we have, it's kind of like a ratio. We're looking for the number of the same moles of acid, or H+, I guess let's do that. We want the same number of moles of, H+ to equal the moles of OH. That's going to be the equivalence point when these are equal. And if these are equal, then we can use some equations that we've already learned. So it's up here. The number of moles of H+ is going to be the volume of H plus that we used times by the concentration of, is that right? Yeah. H plus that we have. And that will give us moles of H. Okay. Moles of hydroxide will be the volume of OH that we used times by, I don't know why I'm switching symbols, times by the concentration of OH that we used. All right. So this is asking us we don't even need to use that actually. We have the concentration of OH. That's the concentration of, let's write this down. We have the concentration of OH. Okay. That's going to be, they give it to us, 0.1400 with 4 significant figures. That's molar. All right. We don't have moles, but we can find moles of H plus using this equation. We have 0.203 grams of lactic acid. So if we divide by the molar mass, so mass divided by molar mass, that will give us the moles of acid. And then we just have to check in. This question can have different numbers of protons. So look at, can you see how this one, we have a hydrogen at the beginning? This will be a 1-to-1. For every one acid, we get 1 hydrogen. So this one, we don't have to worry about that. All right, so that will give us the moles of acid. So that's like this value. We have the concentration. So then we're going to be looking for, this is what we're looking for, the volume of hydroxide that we need to add. So it'll be like an algebra problem. Okay, so let's do this first. So take our mass of lactic acid. I'm going to divide by the molar mass. I'm going to use my Alex calculator. So 0.203 divided by the molar mass. Is it in here? Nope. So we have to calculate it. So we've got 6 hydrogens. So 6 times hydrogen plus 3 times carbon. 3 times carbon plus 3 times oxygen. If you're doing this not on the test and you don't want to practice molar mass, you can just look it up, but we'll practice this time. All right, so that is, we're taking the mass divided by the molar mass of the acid, and this is the number of moles of acid. Okay, H plus. So let's write that down. 0.0022537, and this is moles of H plus, because for every one of these acids, I'll get 1 H plus. Okay, now we have, this is going to be equal to the volume of hydroxide, because we're saying, okay, this is the moles of acid that we have. We want it to be equal to the moles of base that we have. So these two are equal to each other. So the moles of H plus is equal to the moles of base. And we're going to plug in our concentration, 0.1400 molar. So all I have to do now is I'm going to divide the moles of acid by the concentration of base, and that will give me the volume of the base that I need. Oops. So we take this number, divide by 0.14, and then this is my volume in liters. So the volume of hydroxide is, there we go, 0.01609 7. I don't know how many things to write down. Okay, so then let's go to our box. This is asking for milliliters. So the last step is we're going to times by 1,000. 1, 2, 3. And then we have to look for sig figs. How many sig figs did they give us? This number had 3. We didn't even use this number, so we're going to ignore that. So we have 3 sig figs, and we had 4 sig figs in the base concentration. So we're going to go with the least sig figs. We're going to go with 3. So this is going to be 16.1 milliliters of base. Okay. All right, should we do another one? Let's see if we can find one that's more protons. Okay, great. This one's triprotic. Phosphoric acid. All right. Questions so far? Just do another one. So we're looking for moles of acid because we need to relate that to moles of base. We want that when they're equal, and then we can relate to how many moles of base through this equation. So we're going to find the moles of acid by taking the mass of the acid, grams of phosphoric acid. We're going to divide by the molar mass. And this is going to give us the moles of acid. So let's do that. 0.0719 divide by the formula. We have 3 hydrogens, 3 times hydrogen, plus phosphorus, plus 4 times oxygen, this is the number of moles of acid. 1, 2, 3. Oops, I wrote an extra one. 7, 3, 3, 7, 1. Oops, 3, 3. 7, 1. So this is moles of H3PO4. How many H's can I get out of this? How many acidic protons, hydrogens? There's 3. This is a triprotic acid. So that means for every 1 mole of acid, I'm going to get 3 hydrogens. So I have to multiply this number by 3. Okay. So that's really important. Do you guys catch that? If this is a triprotic acid, I have to multiply the number of moles of acid by 3 because I get 3 hydrogens for every 1 mole of acid.
What if that has 2?
Then you'd multiply by 2. If it's a diprotic acid, then you multiply by 2. Okay, so I'm going to multiply by 3 because this is a triprotic acid. Times by 3. I'm going to need, so just like in the last question, I needed 2 acids to balance, like calcium hydroxide. This one I'm going to need 3 hydroxides. So I'm
What
for every
if the hydrogen atoms are spread out like in
acetic acid?
yeah.
So acetic acid will only have 1. This question is going to help you. It will tell you. So if it doesn't tell you, there's only 1. But you can look if the hydrogens are at the beginning, those are the acidic hydrogens.
But if there was another hydrogen somewhere else, then it would be.
You're right. Yep. Yep. Just like the last one we had, there are some hydrogens in the middle. Those ones won't be acidic. Those ones. Yeah. Those don't come off in solution. Yeah, they're more attached than the other ones. Yes. Yes. Okay, times by 3. This is the number of moles of H plus now. Okay, so moles of H plus. 0.00222011. Okay, so then this is equal to the volume of the base times by the concentration of the base. Because remember, volume times concentration gives us moles. We want to have equal volumes or equal moles. equal moles of base and acid. So if we set these equal to each other, we can figure out the volume of the base if we plug in the concentration. So our concentration of our base is 0.1700 molar. We're going to divide by the concentration of the base. So now the volume of the hydroxide, the base that we need, is this value divided by 0.17. So we need 0.012947. This is liters. So remember, moles divided by, this is molarity. This would be like moles divided by moles per liter. So we would flip and multiply. So we'd cancel out moles. We have 1 over liters, which would flip and get, we'd like multiply by liters over 1, and we'd get liters. Oops, that didn't help. So our unit is liters. They're asking for milliliters in this question, so I'm going to move my decimal place. Oh, where is my mouse? Move my decimal place 3 to the right. 1, 2, 3, multiply by 1,000. And my answer will be 12.9. I have 3 sig figs here. We never use the volume. This is 4 sig figs, so we're going to use 3.
Wait, I thought it says there shows that you times the volume by the concentration.
We do not have the volume of, yes. We don't have the volume that we, let's see. We have the volume.
Yep.
I guess we could also find the concentration. We could do it that way. I think this way is easier because you can just find the moles. So it's like all of these things are equal. So what we're doing is we're replacing this with this. We're saying these are interchangeable. So we're going to use this. Yeah, you could do that to find the volume and the concentration. But ultimately we just need moles. So if you do it this way, you're just calculating moles. So this is a faster way to do that. Yeah. Yes. All right, if you don't need to do this, you can work. We're going to do one more. All right, so this one is, there's extra hydrogens in this one, but we only care about this first hydrogen. That's only acidic hydrogen. So we're going to take our mass. I'm going to divide by the molar mass. And I'm going to look for moles of acid, or this acid is acrylic acid. So 0.116 divided by the molar mass. So let's see, we've got, oh man, 4 hydrogens, 4 times hydrogen plus 3 carbons one, 2, 3 carbons, 4 hydrogens, and 2 oxygens. Let's see if that looks right. No. 4 times hydrogen, 3 times carbon, and I just have 1 oxygen. I need 2 times 2. Oh, this is multiply. Plus 2 times oxygen. Okay, that looks right to me. All right. This is going to give me the moles of the acid. I'm going to look at my acid. There's only 1 acidic proton, so I would be multiplying by 1. I'm not going to do that. There's only 1 hydrogen for every 1 acid molecule, 1 of the acidic hydrogens. Okay, the next thing I'm going to do is I'm going to take this and I'm going to divide by the concentration of base. So if we have the moles of hydrogen, then that's going to equal, so moles of hydrogen divided by the concentration of base gives us the volume. Oh, thank you. Gives us the volume of the base. And then we have to convert to milliliters, so times by 1,000. This one will be 8.47. 8.47. I need 3 significant digits. 8.47. Okay. So this one's not too tricky if you know what you're doing, if you can figure it out. All right, we have 15 minutes left. I will let you work and I can wander around. Next time we're ahead. So we're gonna just have some work time, and we'll also talk about lab 8. So we're gonna have lab 8 at the end of next week. I think you guys will actually, so on Tuesday when we come back from the 4-day weekend, we will have lab 8. So yeah, next weekend is a 4-day weekend. Not this weekend, next weekend. Because of President's Day, and the teachers have a comp day. Yeah.
What day is next Friday?